This won't be long. This really won't be long. Okay, so last thing I want to go through. Close them up real quick. I'll get you back to them. So the last thing I want to look at is for rational functions, we want to look at the end behavior. Let's quickly just kind of recap what we've done. So for rational functions, we have found ways to find vertical asymptotes, right? We know where to find zeros, and so we know how to kind of get a basic skeleton for what the function looks like. I want to look at. Okay, yeah, and we looked at one yesterday where we had a hole, right? Remember, that's where we left off. Okay, we got to review one thing. So how do we know, like if we take this function that we looked at yesterday, right? This is the last one we looked at. We want to find the values of x that are omitted from the domain, because remember, we can't divide by 0, right? So which values, well, okay, why did we exclude those two values from the domain? How did we come up with these two values? These were our domain was all real numbers except x couldn't equal 0 and x couldn't equal -3. Just quick recap. How did we come up with those? Zeros at the bottom. Good. So with rational functions, we're going to find the zeros of the top and the zeros of the bottom, right? The zeros of the bottom are going to be places where we have to exclude those values from the domain because we can't divide by 0, right? Okay, some of those zeros of the denominator could be vertical asymptotes, and some could be holes, and they're very different things, right? Vertical asymptotes are massive changes in the behavior of the function. We call those infinite discontinuities. Holes are really tiny. Holes are just point discontinuities. There's just one missing point. You can't even see it on a graphing calculator or on Desmos, right? What's the difference? How do we know which is which for the rational function? Which one is going to be like, how would I know here, for example, that I'm going to have a vertical asymptote and not a hole at x equals -3? Okay, so it's a 0 of the bottom only, right? If it's an exclusive 0 of the denominator, then that is always a vertical asymptote, okay? Whereas at 0 is a simultaneous 0 of the top and the bottom, right? And so that means when it's a shared 0, that means it's always going to be a hole every time, okay? We looked at one other thing here that was kind of interesting. We said, okay, f of x, algebraically, and this isn't a huge deal this year, but it's a really big deal in calculus. So I want to just make sure that you get this point. F of x, this looks pretty complicated. Algebraically, I've got a factor of x in the top and bottom. If I cancel those, what you got to understand is that I'm getting a new function. It's almost the same as the original one, but it's slightly different. Remember, whenever you cancel a variable, top and bottom, you're losing some information about the function, right? We're losing zeros in the top and bottom. So if I were to go back and algebraically cancel those out and call this just plain old g of x, what did I do to the function? Sam, what did I do to the function if I cancel out those x's?
You get rid of a.
No? Anybody else want to pitch in here? What do you think?
You fill in the hole.
Fill in the hole. That's it, right? I fill in the hole. Okay, so that's the only thing different, but it is a different function. It looks the same every place except at that one spot where I physically filled in the hole by canceling out those x's. Okay, so this is a strategy in calculus when we're trying to, and once again, I'm jumping ahead, but for you guys, I want you to kind of just have a vision a little bit of where we're going with this in the future. This is a strategy we have. If we're trying to find the limit of a function that is not defined at a certain value, then sometimes what we'll do is we'll trade the function for a new one that fills in the hole, right? So we'll come back to that in a couple of years, and we'll talk a lot more about it, but that's just so you kind of get a glimpse of where we're going with that, right? It really does change the function, though, because it now all of a sudden now for g of x, 0 is a part of the domain, isn't it? Right? Okay, so last thing we have to cover is what the end behavior does. We know how to find vertical asymptotes and holes, but what about the end behavior? Let's start with this one right here. what do you predict is gonna happen with this? I think this is kind of interesting stuff. So, I'll make this a little bigger for you, how about? So what do you think? What do you think's gonna happen there? If I take, and by end behavior, remember, it's been a while since we've talked about that, but end behavior means the behavior at the ends of the function. So very, very far off to the right or very far off to the left. As x approaches, probably what values? Infinity or negative infinity, right? So what do you think's gonna happen? It's gonna get closer to 2, you're right. How come? Okay, so if we were to, let's say, divide this out. Okay, there's a couple ways I could do this. Let's say I'm just gonna take this quotient and just divide it out. Okay, so what do I get if I do that? We have to use long division, right? Because we don't have a linear factor on the bottom. So this is just a good brief review. What do I have to put? So when I'm using long division, how am I going to write the polynomial that goes inside the integral sign? Okay, good. Exactly. Remember, I preserve a column for every power of x. Okay, so then how about here? Duncan, what's going to be my first term? Why don't you guys put your phones away, please? So x squared divides into 2x squared how many times? 2. Okay, so then I'm going to distribute that through, right? I'm going to get 2x squared plus 2, and I'm going to subtract that away. What do I get? Those cancel, nothing there. 5 minus 2 is 3. So my answer is 3, oops, half a here, 3. Oh no, 3 is the remainder, sorry. So I get 2 plus a remainder of 3 over x squared plus 1. Okay, that's helpful though to us when we're taking our limit. This is a much easier way to write the function, right? If I want to take a limit here then, so the limit of f of x as x approaches plus or minus infinity, it's not going to matter, is going to equal the limit of this function. Right, and this is the notation that we'll use in calculus. Okay, what's going to happen to that limit? As x gets really, really big, does that have any impact on the 2? No, the 2 is a constant, so that just stays there, doesn't it? Right? And you're getting a little bit of insight. Once again, this is good. You're seeing limits here a little bit in a real sense. What about this term right here? As x gets really big, positive or negative, what's going to happen to that fraction? Yeah, look, the top is fixed at 3, isn't it? But the bottom is going to be increasing without bound. So the denominator gets huge, and what happens to the behavior of a fraction if the top stays the same but the bottom grows infinite? Yeah, it goes to 0, doesn't it? Right? And so the answer is 2, okay, just as predicted. That's our limit. As the function goes to infinity, the value of the function, the y value, is going to approach 2. Now, how could we maybe have seen that? And Hilton gave us a little hint here already. We could maybe predict that behavior, because if you look at the behavior of the leading coefficients here, 2 over 1 is going to give us the end behavior of the function, right? Okay, there's another way you can think about this. Remember earlier in the year when we took an example of a polynomial? I think it was like a 4th degree polynomial, and we started off, zoomed in really close, and it looked linear, right? And then we zoomed out a little bit, it started to look quadratic, and then it started to look cubic, and then ultimately, even though the coefficient of the x to the 4th was really tiny, eventually that took over and became just purely quartic, right, 4th degree. We know that the behavior in a polynomial, as x gets really big, only the leading term contributes. Everything else is just insignificant, right? So really all we have to do, in a sense, is just think of this. Whoops, I went back too far. There we go. So all we really have to do is just look at these two terms. And if I divide those two terms out, the x squareds would cancel, wouldn't they? Right, and I just would get 2. Okay, so there's one rule. If you're looking at the end behavior of a polynomial, if the polynomial on top, or we have a rational function, sorry, if the top polynomial and the bottom polynomial are of the same degree, so they have the leading terms have the same power of x, then all it is just the ratio of the leading coefficients. Okay, and if we look at, if we were to go, if we were to look at the graph of this thing, that's what we'd see. Okay, notice that the asymptotes, the horizontal asymptote is at x equals 2, right? Just like predicted. So we've got that horizontal asymptote that acts at both ends. Okay? How about, let's look at another one. So what about something like this? What's your prediction going to be there? I can't divide this one out, can I? The bottom doesn't even go into the top. Now think about this. This is a bizarre concept. As x approaches, just say positive infinity, although negative infinity would work also. The top and the bottom are both approaching infinity, aren't they? Which one's approaching infinity faster? How much faster? Infinitely, right? The bottom, they're both approaching infinity, but the bottom is approaching infinity squared, which is infinitely faster than the top is approaching infinity. And so what do you think is going to happen? What do you think the end behavior is going to be there? No. The f of x is going to approach what as x approaches infinity, do you think? No, let's look at it a different way. I got another way I can show this to you. Here, it's going to approach 0. Okay, let's do this. Let's take, here's another strategy that'll prove this to you. This is, let's say we're going to divide both the top and the bottom by x squared, which is the same thing as just factoring an x squared out of the top and the bottom, right? So if I were to divide the whole top by x squared, term by term, what am I going to get? X divided by x squared is what? X divided by x squared. 1 over x, wouldn't it be? Right? 3 divided by x squared would just be 3 over x squared. Right? What about on the bottom? X squared over x squared is 1. X over x squared is 1 over x. 6 over x squared is just 6 over x squared. Now, if I took a limit of this whole thing, right? So, oh, there we go. Okay. I'm going to get the limit of this, right? We rewrote this function in this form. As x approaches infinity, what's going to happen, or negative infinity, what's going to happen to the fraction 1 over x? What's that going to approach? 0, right? Because the bottom of the fraction is exploding, the top is staying the same at 1, right? So that goes to 0. What about that? 0. That stays the same, right? That goes to 0, that goes to 0, and so what do we get? 0 over 1, well, what's 0 over 1? 0, yeah. Okay, so what's our rule? And here's your thinking on that. Here's kind of how you can conceptually, attach that. You know, it's because the bottom has a bigger power of x, so it's growing much, much faster. The top is getting big, but the bottom is getting infinitely bigger, and so it's going to dwarf the growth of the top, and you still end up with a fraction that approaches 0, right? So there's our second rule. If a rational function has a denominator with a bigger degree than the numerator, then the end behavior is what? I get a horizontal asymptote at y equals 0, okay? 2 rules, all right? And this is what thought I had it. Oh, there it is. Okay, and that's what this one would look like, right? So notice the end behavior. We've got this horizontal asymptote shared at both ends, y equals 0. Okay, last case. Make a prediction for me first. Yes, sir.
Why does it cross the x-axis?
The function you mean?
Yeah.
Right here? Okay, so yeah, so the question is why does it cross the x-axis? Because I think, and I know where that's coming from, because with a vertical asymptote, does the function typically cross the vertical asymptote? It doesn't, does it, right? We looked at all these examples of functions and they'll butt up against it, but they can't cross it. Because if they crossed it and went back, that wouldn't be a function. It'd violate the vertical line test, right? So you don't cross a vertical asymptote. You just don't. But a horizontal asymptote, it's fine. You can cross a horizontal asymptote. All the horizontal asymptote is, say it again?
I thought the asymptote was something you couldn't cross.
No, the vertical one. Horizontal one, the horizontal one's a little bit different. It accomplishes kind of the same thing. It tells you what eventually the end behavior is going to approach, right? But it doesn't necessarily mean that you can't cross it. A lot of times we don't, but I'll give you an example of a function that crosses an infinite number of times. What about something like, you guys haven't done trig stuff, but if we did, for example,
We get a full work day
Can
tomorrow.
we work?
yeah, you do.
We have tomorrow or two. We just said that.
I'll give you tomorrow to work.
I think we should get the rest of the year.
What if, no, that's not gonna happen. So what if we did something like, you guys don't know what this looks like, but you'll see this next year, a sine function.
Wait, I have a question really quick.
Yeah.
So are we supposed to find like if lines cross, like where they meet?
But you mean the
Are we
asymptotes?
supposed to do that? Yeah.
No, you don't need to.
Oh, okay, because I was gonna be like, well, what if like one of the lines is a hole? How are we supposed to figure out if it goes in a hole?
Okay, listen please, good question, go ahead.
Like, no, but if we don't have to find where they cross.
No, you don't. All we're gonna do is we just wanna find, no, it was good. Here's what this function would look like. This function would look like this. This function would just look like, right, it's just gonna wiggle in either direction. I just wanted to give you an example. So, I mean, it crosses an infinite number of times, but the asymptote is still useful because as we go infinitely far in either direction, it tells us what value it's going to approach, right? Yep.
Your drawing of it
Is very incorrect?
yes.
Okay.
Let's just not ask questions.
Oh, hang on.
I just want to.
What does it just look like this?
Oh, it goes backwards. Yeah, you're right, it is. It's gonna oscillate in the middle a whole bunch. Yeah. I'd want to do something, here's what I want to do, here's what I meant to do.
Very close up view, okay?
Yeah. I meant this.
No, thank you.
Something like this.
You're on black.
Oh, come on, black, that's not gonna work. That's what I wanted to do. 1 over x times sin x. Try that one out. Does that look good?
Yeah.
Looks good? All right, there we go. Okay, so, okay, last one.
You said that.
Okay, now hold it. Hey, listen up. I will try to give you as much as you can, but this is an honors algebra 2 class. We're gonna do this, enough's enough. We're gonna do this at an honors level. I'm gonna give you some work time, but
As long as I pass, I'm good.
you're going to. But consider that in the future if you wanna be in a class like this, I guess. But this is a different level than algebra 2. And that's just the way it's gonna be. I'm not gonna, okay, I mean, I try to give you as much time as I can, but come on now. I mean, I have to, I mean, I've got a prerogative here to get you ready for higher level math classes too, right? So please understand that. Okay, so what about this? What do you think? Yeah, so we know as x approaches infinity, what's gonna happen this time, do you think? If the top is a bigger power than the bottom? It's gonna get bigger forever, isn't it? Because the top is growing faster than the bottom of the fraction, right? Okay, so we know it's gonna explode, but how is it gonna explode? Okay, one thing we could do here, we could take advantage of, and we'll talk a lot more about this in a couple of years, and I don't wanna go into too much extra stuff here, but the one thing I do want to talk about is, what do you think is going to happen if we divide a quadratic function by a linear function? Now think about that. What's going to be, I'm going to get something left over. What do you think the power is going to be? Okay, yeah, we're going to end up with an x to the 1 in there, aren't we? Right? Does that make sense? Because if I just think about, and here's kind of the way you can conceptualize this. Now, we talked earlier about when we divide polynomials, and if we're talking about end behavior, right, when x is getting really big or really small, the only terms that matter are the leading terms, right? So when x is really, really big in the positive or negative direction, the x squared is going to dominate everything else in the top polynomial. The x is going to dominate the 1 in the bottom polynomial, right? So if I look at the ratio of just the leading terms, what are we getting? X squared over x is x. Okay, so there's going to be, so we know that this is going to behave, it's going to behave in a way where it's going to explode, because if x is left over when x is approaching infinity, then the function is approaching infinity, right? Does that make sense? Okay, let's divide it out and see what we get. This is one where I can use synthetic division, so it's really quick. The bottom is linear, right? It's got an x plus or minus a number, so it fits our synthetic division template. What number goes in the bracket? Okay, what are my coefficients on top? No. 1, 0, negative 4, good. And then bring the 1 down, what do I get? Negative 1, 1. So I get a remainder of negative 3. Everybody agree? Okay, so let's write this in two parts then. F of x looks like a linear part, which is, this is the constant and that's the coefficient of x, right? So it looks like x minus 1 plus a remainder of negative 3 over x plus 1, right? Okay, now in the limit that x approaches infinity, what's going to happen to this last term? If I let x approach positive or negative infinity, what happens if I have an x on the bottom but not on the top? What's that approach? 0. Okay, so if I take a limit of f of x, that term's going to go away, and what do I get? I just end up with the function x minus 1. What do you think the asymptote looks like this time? As x gets infinitely large or infinitely small, what's the line it's going to stick to? Now, all the ones we've looked at in the past have been either vertical asymptotes, right? Or we just introduced this idea of horizontal asymptotes. But if the degree of the numerator is 1 bigger than the denominator, look what we got when we divided this out. We got a line plus a leftover term that's going to vanish. So what's the asymptote going to look like this time? It's not horizontal and it's not vertical. Yeah, it's slanted, right? This is what we'd call a slant asymptote, right? And so if we wanted to define what this looks like, here's the picture. Now I'll let you work on it. I want you to see this though. See, it looks like that. What's the asymptote look like here? Well, what was our line? X plus 1? Was it x minus 1? Minus 1? So there it is. So it's just going to be that line right there, right? If if I went far enough out to either side, I didn't draw that very well, but the function would just gradually adhere to that asymptote. Okay? So it gives me the large scale behavior. Make sense? All right, so I'm going to resist the temptation to go through another example with you. I think you're fine. All we're going to do on these, remember, is we're going to define the vertical asymptotes and holes. We're going to get the end behavior, which is either going to be a horizontal asymptote or maybe a slant asymptote, right? Or eventually, we'll only look at those cases. And then I'll draw the asymptotes on first, and then all I have to do is just decide how the function fits to the asymptotes by taking the limit as x approaches a certain value or something, right? Are we good? You good to go without me doing an example?
Yeah.
I think you are. Okay. Go. Your assignment, there's a paper assignment up there for 8-2.